At the moment, there are literally 5 different ways to train a Stable Diffusion model to understand a specific concept, like an object or a style. We've got Dreambooth, Textual Inversion, LoRA, Hypernetworks, Aesthetic Embeddings. I've done videos on all of them, and today we're going to work out which one you should use. Okay, so to answer that question properly, what I went ahead and did is I read all the papers, I trolled through the automatic 111 codebase, I scraped a whole bunch of data off civitai to see which models people are liking and what they're not liking. I compiled a big spreadsheet, I made a nice diagram, and today we're gonna answer that question. That's what we're gonna do. At the end of this, you will know which one you need to use. By the way, if you like that video there, this was made by someone called Dreaming Tulpa, who seems to be very good at AI art. So if you want to follow that person on Twitter, it'll probably be a good idea. But I digress. This is how we're going to structure this video. What are the methods and how do they work under the hood? That's the first question we're going to answer. The second question is, what are the trade-offs? You know, according to the data, which ones seem like they're better and which ones have which kind of benefits and which kind of downsides. That's how we're going to structure it. Okay, so there are 4 methods. We have Dreambooth, Textual Inversion, LoRA, and Hypernetworks. There's actually a 5th method out there. It's called Aesthetic Embeddings. I did a whole video on Aesthetic Embeddings. Here's the thing about Aesthetic Embeddings, they're not good. They don't give you good results, they're bad. So don't use Aesthetic Embeddings. That would be my suggestion, and because of how little respect I have for Aesthetic Embeddings, I have taken them out of this video, and hopefully that won't get clipped in like 5 years when Aesthetic Embeddings is ruling the world. All 4 methods work in very similar ways, but we're going to start with Dreambooth because it's probably the most straightforward. So the way that Dreambooth works is by actually altering the structure of the model itself. I made another video on what happens when you do this badly, which is kind of fun to check out, I think. In Dreambooth, you have 2 inputs that you have to be concerned with. First input is the concept that you want to train. So in this case, we have this picture of this corgi. In reality, you might have 5 different pictures of the same corgi because you're trying to train the model to recognize that corgi. And on the other hand, what you have is this sentence, which has something called a unique identifier in it. In this case, this SKS thing is the unique identifier. And the whole idea of Dreambooth is that you teach the model to associate this unique identifier with that concept of the corgi. That's what we're trying to do. We're trying to get an association between this and this. That's the plan. So, sort of drilling into this a little bit more deeply, the way this works is that you take your sentence and you convert it into a text embedding where each word is represented by a vector, what's called a vector, but that's basically just a list of numbers or an array of numbers. And the numbers are usually like floating point numbers. They're 0 point something, something, something. And the idea is that each word has its own unique vector, and the vector, you know, contains some semantic information about the word. We're not going to delve into embeddings at the moment, but the idea is that, you know, this vector contains some information about the word. This vector contains something about photo, and this one that's associated with SKS will be quite random and it won't have any meaning because, of course, SKS doesn't really have any meaning in the English language. And the idea is to associate this concept with that new vector that doesn't really have any meaning. Okay, and the way we do this is that we pass in the text embedding, and then we apply a whole bunch of noise to the sample image until it's quite noisy. And then we also apply a little bit less noise, right? So we might first apply 10 steps of noise to the one that we're going to pass in, and then we also create another one which only has like 9 steps of noise applied to it. And we're going to try to get the model to take the 10 noised one and output the 9 noised one. That's the idea. So we put in the 10 noised one with this text embedding, and we say Stable Diffusion, denoise this image and return it to what it usually was. Now, originally, because the model doesn't know what the photo's of, you just said photos of SKS, the model looks at that and goes, well, I don't know what an SKS is, and it'll probably do a pretty bad job. It'll probably output not a photo of the corgi, a bit denoised, instead it'll output something crazy. In SKS, it might output a sort of sign or some text or something. And then what you're going to do is you're going to compare what it outputs to the 9 noised output, the one that was supposed to create, right? So you've given it this very noised one, you've got a slightly less noised one, and you're expecting it to produce the slightly less noised version of the same image. So you compare them, you create a loss. Depending on how separate they are, the loss will be really high if they're very separate, and if they don't look like each other at all. Loss will be very low if they look exactly like each other. And then you perform something called a gradient update, which that is a whole can of worms. But basically, you punish the model if the loss is high, and you reward the model if the loss is low. So having done this a few times, the model will start to get an idea, okay, when I have this SKS thing thrown at me, when that SKS thing comes through, it has to look a bit like that corgi that they keep passing me. So okay, I'll try to make this image look a bit like the corgi. And of course, you have like 8 different images, so it can't just narrow in on one single image. But eventually you get a model that you can pass in noisy images and this SKS thing, and it'll try to denoise them and turn them back into a nice clean image of a corgi. That's what you'll eventually get. So that's how Dreambooth works. And that took a long time to explain, but hopefully we're kind of all on the same page on how it works, and we can use this model to understand how the other techniques are going to work. The important thing about Dreambooth is what you're actually doing is you're creating a whole new model. You have your initial model, and you make updates and change the internal structure of the model until it understands this concept. And because of this, and for reasons that I'll get to later in the video, this is probably the most effective means of training a particular concept into Stable Diffusion. Dreambooth is probably the best, and there is some evidence for that, but it is pretty storage inefficient because every time you do Dreambooth, you have a whole new model just sitting out there, right? So you train your corgi, great, now you have 2 gigabytes of model to deal with, and you have to remember that's the corgi model. And then maybe you also want to train your cat, then it'll be a cat model, it'll be 2 gigabytes. Of course, it is possible to train multiple concepts into the same model, but sometimes that'll actually make the model get a little bit confused. So basically, these big models that you have to carry around, these 2 gigabyte files that you have to share around and stuff, they're sort of the downside of Dreambooth. But other than that, it's probably the most effective method. Next, we have textual inversion. And we can see that basically the setup is identical, right? There's not much difference. We still have this SKS thing, we still have our corgi, and we're still trying to teach this setup to learn how to output the corgi at the end of it. And we still do exactly the same thing with the denoising to the 10 and the denoising to the 9 and then comparing and making a loss. The difference with textual inversion, and to me this is the coolest one actually, is that rather than performing a gradient update punishing the model when it doesn't get the right output, you actually update this vector over here when it doesn't get the right output. So what you're doing is you feed in the embedding, you feed in the noise, the model does its thing, it outputs an image. At the beginning it'll look nothing like the corgi, and then you penalize it for not matching the slightly noised, the 9 noised image, and with the penalty you perform a gradient update on the vector instead. You don't perform the update on the model, you perform the update on the vector, and slowly, the vector gets closer and closer to the visual phenomena that you are looking for, which is this corgi. And eventually you'll almost have this corgi vector, which knows exactly what this corgi looks like and can be used to describe that corgi perfectly to the model. And the interesting thing about this is that it doesn't seem like it should work. With Dreambooth, right, you can tell how this would work, right? This model is a very complex model. It can understand thousands and thousands of concepts. We're just introducing a single other concept into this model. You know, this SKS thing, we're just associating this with that. Easy, you know, that's the kind of thing that this kind of Dreambooth model is very clever. It can do that in its sleep. With textual inversion, it's really not obvious that it should be possible to just create a vector that is so special and so perfect that it tells the model about this corgi that the model's never seen before in its life. But it turns out the textual inversion, it does actually work, like really well. So textual inversion is very, very cool. When you're training, you don't update the model at all, you just update this vector. And the big benefit of textual inversion is that the output isn't a whole new model, which is worth 2 gigabytes. Instead, you end up with a tiny little embedding, which is like 12 kilobytes or something. And with this embedding, you can give your embedding, you can share it all over the internet, and someone can just download their embedding and then plug it into their model, and they'll also get that corgi. And again, I cannot express how cool this is. It means that these models have such a nuanced understanding of visual phenomena that just by creating the perfect vector, you can generate arbitrary visual phenomena that still make sense to humans. So textual inversion, it's the coolest in my opinion, although Dreambooth is probably slightly more effective. Next, we have LoRA, which stands for low rank adaptation. It's also actually really cool, but in order to understand exactly what's going on here, we're going to have to look inside the diffusion model itself and how it works. The way neural networks today are set up is as a bunch of consecutive layers. So in this case, we have 3, often there'll be, hundreds. And what happens is you take your input, which is usually a big matrix of numbers, and you pass it to the first layer. And the first layer will do some sort of calculation on that big matrix, and it'll spit out another matrix, which I've made small just to make it nice and visually appealing, but it would also, this would be usually huge. And then this intermediate matrix is passed to the next layer, which then does a bunch of calculations and spits out yet another sort of transformed matrix. And finally, you pass it to the last layer and then you get your output. And the idea is that as these weights, these outputs get passed through the model learns more and more about the structure of what was in the input originally. And by the end, it knows exactly what was in the input and it knows exactly the precise thing to give you in the output. That's basically how neural networks work. So where does LoRA fit into all of this? Well, LoRA is actually trying to solve the Dreambooth problem. So remember, with Dreambooth, you have this new concept that you're trying to teach the model, and you train the model and update the model until it learns the new concept, and then you're left with a new model, which is like, it's big, usually. You have this big model. And this is the problem that LoRA is trying to tackle. They want to be able to teach the model a concept without having to make a whole copy of a model. Because Stable Diffusion isn't a very large model, Dreambooth is actually okay, and you can still kind of use it. But originally, LoRA was being used for large language models, which are like immense, which have like billions and billions of parameters. And they're really not feasible to make a copy of every time you want to train, a new little subtask. So what LoRA does is it simply inserts new layers into the model. So originally the model looked like this. It had 3 layers and then 2 intermediate states. And now the model looks different. It has 2 extra layers in there, and it has now 4 intermediate states. So input goes to the first layer, layer makes an output. Output doesn't go directly to the second layer, it goes to the LoRA layer, which then outputs the second intermediate state, which then goes to the middle layer, and so on. So basically you just insert new layers, and these layers are like tiny. They're like tiny layers. And by default, these layers are they're set up such that they won't impact the model at all. So like when LoRA training starts, you end up with just blank layers that output exactly the same thing as they input. Then as training proceeds, and with this loss, you update those intermediate layers so that they start outputting slightly different values as the information passes through. And that happens to all the LoRA layers. So slowly, as these layers become more and more opinionated, the outputs that are actually running through the model, these intermediate states, will end up being quite different from what they were originally. And, once you do this a lot and you update the intermediate states enough, eventually you'll be able to do what normal Dreambooth training can do and actually get the model with these new layers in it to understand the new concept. So that's how LoRA works. It's kind of like Dreambooth, but rather than updating the weights that are already there, you sort of add in new weights and update those new weights to achieve exactly the same effect. And again, you're using the same gradient update process. So you pass in the prompt, you pass in the noisy image, and we compare the output to the output that we expect, and then we have a loss. And if the loss is huge, then the LoRA layers get updated a lot, they get sort of punished. And if the loss is small, or it's like a good score, then the LoRA layers get rewarded. And slowly, the LoRA layers learn how to make the model output the correct output. Okay, so what's the upshot of LoRA? Why wouldn't we just use Dreambooth? Well, firstly, LoRA training is a lot faster and takes less memory, so that's a big benefit. And also, LoRA layers are very small, and you can sort of pass them around and add them into different models and share them much easier than you can the full model. I think usually the LoRA layers end up being about 150 megabytes compared to 2 gigabytes for the whole model, so they're a lot more compact. There's also some really good math behind why LoRA layers work so well, but we're just going to leave that to the side for now. So that's the benefit of LoRA. Basically, as far as we're concerned, it's just quick to train. And finally, we have arrived at Hypernetworks. These work basically exactly the same as LoRA. There's no official paper for the Hypernetworks, as far as I'm aware, at least not one that talks about Hypernetworks in any context that's similar to the Stable Diffusion models. But this is information that I got from reading the automatic 111 codebase, and this basically seems to be how it works. again, you have these intermediate layers inside the model, but instead of directly updating these intermediate layers and optimizing them, you have a model called the hypernetwork, which it outputs the intermediate layers. So just like the Stable Diffusion model will output a matrix of numbers, which we then interpret as an image, the hypernetwork will output several matrices of numbers, which are then used, those matrices, as intermediate layers inside the diffusion model. Exactly the same idea as LoRa. You're sort of inserting these additional layers into the network, and they're updating and getting better and better at giving you the output you want. But rather than updating the layers directly, compared to the loss, you're updating a network that learns how to create these layers, and the network gets updated and updated, and this is the one that becomes cleverer. And that's hypernetworks. They haven't actually been extensively studied in the context of Stable Diffusion, but my intuition, which could be wrong, is that hypernetworks are just sort of a worse version of LoRa, because there's a whole bunch of clever math stuff that happens in LoRa to make these inserted layers like really easy to optimize and easy to train and just good. And I suspect that doing it indirectly through a hypernetwork, another model that learns to build those layers, my suspicion is that's probably a bit less efficient and less good. But it does sort of have the same benefit. In the end, you end up with about 150 megabytes worth of stuff to pass around, as opposed to 2 gigabytes of the Dreambooth model. So it's quite similar to LoRa in that respect. Okay, so that took a long time, and I don't know about you, but my brain is kind of fried from that, and my vocal box isn't working anymore, but I get to put a tick here now, because we've now seen the underlying information, and now let's get to that juicy data. Done the qualitative, now we're gonna do the quantitative. Okay, so this spreadsheet contains a whole bunch of information just based on my own research about important facts about each training technique. So like how much RAM it takes to train, how many minutes it takes to train, etc., etc. So go have a look at those things. The main takeaway is that they all take about the same amount of training RAM, which was very surprising to me, but apparently they all do. They take very different amounts of time to train, and the output sizes are like very varied, with textual inversion being like really tiny compared to the others. The other thing that this spreadsheet contains is a whole chunk of data downloaded from civitai about how much people like and use different models. And civitai, by the way, quick shout out to civitai. They're amazing. Use civitai, do it now. It has a whole bunch of models and embeddings and checkpoints and stuff that you can download and try, and a lot of them are really good. So civitai, good, use. So I went ahead and generated a bunch of summary statistics about which models are like the most popular, etc. And I made them available in this spreadsheet. So all this data is based on the top 100 models for each category on civitai. So for instance, average downloads of the top 100 models of Dreambooth, how many times on average have they been downloaded by users? And on average, it's 5,000 times compared to 427 for Hypernetworks, etc., etc. So basically, the main conclusion that we get from this data is that Dreambooth is by far the most popular. So Dreambooth has by far the most downloads, ratings, and favorites. And because of that, it doesn't necessarily mean that Dreambooth is like a really good model, but it does mean that lots of people are using it. And that's a big benefit in and of itself, because it means that there are going to be more resources on that model. There's going to be more models out there for you to use. If I really needed to teach a model a concept right now, I would use Dreambooth just on that basis, because I know there'll be better tutorials, there'll be less hunting around in, forums for stuff. It'll probably just work pretty well, because people seem to be using it a lot. When it comes to the actual rating though, Dreambooth and Textual Inversion seem to be out the same, which is kind of interesting because when I talk to people, I tend to hear that Dreambooth works like a bit better than Textual Inversion. But according to the civitai statistics, people seem to like those models about the same. The other two have a lot lower of a rating, which is quite bad news for Hypernetworks, in my opinion. Just on the basis of how poor this average rating is and sort of how few downloads there are, I would say that Hypernetworks is probably a strategy to avoid using, and only use it if you have no other reason and there's nothing else you can do. It also is a bit damning for LoRa, but the thing about LoRa is really new, And there were actually only 11 LoRA models in this data set that I used to take the statistics from. So these numbers here may not be like super indicative of how well LoRA can perform. So, in conclusion, probably just use Dreambooth. It's really popular and people like it a lot. There are only two sort of trade-offs to keep in mind. Firstly, the large size of Dreambooth. So if you're really concerned about size, you want to make like tons of embeddings, like hundreds of embeddings, then maybe textual inversion is a bit better because again, it's quite popular, it's very well liked, but the outputs are very small and they're easy to swap around. So that's one reason you might use textual inversion is because of the flexibility. And there is also a reason to use LoRA in my opinion, and that's the short training time. So I don't know exactly what your workflow is, but I know that when I'm trying to train one of these embeddings, there'll often be like a lot of iterations before I get the embedding right. And when your iterations take 15 minutes as opposed to 45 minutes, that can be like a huge benefit. Okay, so those are the trade-offs. I can now put my nice big tick in that box and I am done. So tomorrow there's a live stream. You can join it if you want. There are thousands of links in the description, literally millions of links about different places you can go if you want to learn more about any of the things that I have said here today. And there are great people talking about all these things and it's all good. And there's also a Discord if you want to join it. And if you have any questions, you can go to the YouTube comments and that is all we have. And you good luck, okay? Because there's a lot of information. I hope you do something with it.